Typed recursive functions are only one half of the story with typed recursion. We'll also want to define recursive types to write interesting programs. First, let's step back. If we look at the different forms of data that we have right now and how they interact with types, we've seen a few categories. First up is the atomic category. Atomic data includes numbers, booleans, and so on. Next up, compound data. This kind of data groups things together, and it includes tuples and records. Third form, which we've been using all semester in Splate, is variant data. Variants describe a choice among a finite number of possibilities. Here are three quick examples from Splate. First, we have a grade type, and there are two variants, two possible kinds of grades. A grade is either a percent with an integer field, or a grade is a pass-fail with a Boolean field. These next examples are a bit more contrived, and that's because these type definitions are as simple as they can be. They all follow the form where they have two variants, and each variant has one field. And that's because the simple version is the one that we're going to implement for Mo. First up, we have a chain type, and this is a useless kind of list. A chain is either an end, which has an int inside, or it's a link, which just points to the next element in the chain. So every chain has one int wrapped up in some number of links. Next up is a slightly more useful type, int list. An int list is either an empty list, which has one int inside, or it's an icons. And the field inside icons is a tuple, which combines an int with another int list. So this empty case is not exactly empty, but that's again because we're forcing every variant to have exactly one field inside. The plan now is to add the simple type definition to Mo. But before we do that, it's worth asking, could we encode type definitions? For the simple grade type on top, the answer is yes. Here's an encoding. With this encoding, we've got our two variants for the grade type, percent and pass-fail, and then we have one function that uses a grade, isPass function. And the way these encoding variants work is that they return a triple with an int, and a Boolean on the inside. And that way, both variants of grade have the same type, so that they can both be inputs to a function like isPass down at the bottom. The first part of these triples is a tag. It's either 0 or 1, and that tells us which variant we're inside, either percent or pass-fail. The second part of the triple is always an int, and the third part is always a Boolean. For the percent variant, the int is the interesting part. The Boolean is a boring dummy value, and here we've just used false. For pass-fail, it's the opposite. The int is a boring value. We have this dummy 0 here, and the Boolean is the interesting part. In this case, the encoding works. We have to use these tags on the outside, and we also need dummy values on the inside, but it works out for grade. However, encoding does not work for our recursive data types. Here's an attempt at encoding chain. The trouble with encoding a recursive data type is that all these red dots need to be the same type, but there's no way to make that work out. We can give this a try. So we'll fill in the dots for end. End takes in an int and returns an int star int tuple. That's fine. Now link should take in something which has the same type as the return type of end, an int star int. It means that R needs to be an int star int, and now our troubles begin. Since R is an int star int, this pair that we construct is a triple, 3 ints, and this is a problem because both these constructor functions need to be returning the same type, but this triple type is not the same as the tuple type. And in fact, the way these types are written, we can't even construct the third link in the chain because this link would need to take in a triple, but right now the link function expects a tuple. We run into the same problem with our int list. Here's how the encoding would have to start off. And so, for recursive type definitions, we will need to extend our language, and we'll extend it with two forms. First is let type. This gives similar behavior to define type, but it looks like a let, and that means we can keep typed Mo as an expression language. We don't need to collect definitions first before interpreting some main expression. Second, a pattern match, and we'll use this to figure out which variant of a let type we're dealing with. Again, let type will have exactly two variants, and each variant will have exactly one field. Here's one example for int list. The two variants are iEmpty and icons, and each of these variants takes one arg. Now, len is a recursive function that takes in an int list and returns an int, which is the number of icons in the int list. This function works by matching on its input and checking if we're in the empty case, then return 0. If we're in the cons case, return 1 plus the length of the rest. Here's the grammar that we'll work towards. Let type and match will both have big structured forms. Let type takes in one symbol name, two variant name, and each variant has one arg. Finally, let type will have an expression body. For match, we have an expression, a symbol for the type of that expression, and then two cases. Each case will have a variant name and an argument name and an expression body. Finally, to support let type, we need to extend our language of types to include symbols. These symbols come into play when we interpret a let type. So the symbol name here at the beginning of the let type, that needs to become a new type name. When we use this type name further down in the body expression, we use a symbol to do so. So symbols need to be able to appear inside of types. With that, we're ready to move forward.